Okay, let me then briefly introduce Paul. Paul is a friend and a mentor. Recently, I met the statistician Jeff Rauder, who told me that you're only known for your best work, typically of him. But Paul is certainly among the people known for their best works in plural. So he has not only made important contributions to the evaluation of Bayesian algorithms. Some keywords here are, leave one out, cross-validation, simulation-based calibration. I can go on. But perhaps most importantly, he's the one who made STAN, and through this probabilistic programming language, modeling to the world of non-nerds accessible. So most recently, he has entered the messier world of simulation-based inference, and more particularly amortized Bayesian inference, about which he will talk in a second, where he has come up with some great ideas on how to align these messier methods to the status of classical Bayesian analysis. And perhaps even most importantly, he has come up with my bad microphones for years, and he's still talking to me. So thank you, Paul. We're very happy to have you here, and the stage is yours now.
Thank you for inviting me. Yeah, so today I'm going to talk about amortized mixture and multi-level models. And so we're going to see that these two are kind of related, and we're talking about how we're going to amortize them. Just let me add that I have the feeling that, the worse the microphones of Stefan work, the better research he's doing. So, if he has a really bad microphone day, the research is going strong. So the team members I specifically want to thank today, because they have very strongly contributed to the work I'm going to present today, is first of all Stefan, who brought me to simulation-based and amortized Bayesian inference in the first place a couple of years ago. And without his strong contributions, both generally in Baseflow, but also specifically to the projects we are presenting here, none of this would have been possible. So thank you, Stefan. Then I'm going to present kind of specifically two papers, one on multi-level, one on mixture models. The multi-level paper was led by Daniel Habermann, a postdoc of mine. The mixture paper was also led by a postdoc of mine, Simon Kocharski. I hope they both managed to enter the presentation here today too. There was some issues with actually getting in. Okay, so thank you for the three of you. Without you, none of this would have been possible. All right. I assume that like a lot or most of you are familiar with the general idea of amortized Bayesian inference, but I'm still introducing it quickly so that we're all on the same page. So the idea in amortized Bayesian inference in a nutshell is that we are splitting the approximation loop, that is kind of, the learning, so to speak, from the inference phase where we're actually going to do inference on new data. So during the training phase, during the approximation loop, we are learning to approximate a posterior distribution from simulated data only. So we are simulating from our prior, we are simulating then from our likelihood, our data, and this goes into an approximator, usually a generative neural network, that then learns to approximate the posterior distribution given any potential data set. So we learn a functional of the posterior distribution given any data set we can put into that. Of course, what we learn properly is only within the space of the data we have seen properly during training. So there's also some big challenges of robustness, of generalization of these kind of amortized Bayesian inference methods that I will not specifically talk about, but this is also something we are working on. All right, so once we have gone through this potentially computational intensive training phase, we are moving to the inference phase where we are taking in any kind of new data, could be simulated, could be real new data, and we are getting the Bayesian inference in an instant like this. Yeah? And when I first heard this idea from Stefan, I think it was 2020, a few days essentially before COVID hit us also in Germany, in a workshop that he actually attended my workshop there, and then he shared the initial Baseflow paper with me and talked with me about this kind of general ideas. I was like, this is really, really groundbreaking in terms of what we can achieve, because what was previously very slow, kind of full Bayesian inference, let's say with MCMC, has the potential to be very, very fast with amortized Bayesian inference, as long as we are making sure that we are training enough and we're spending enough time and thought in the training phase and we ensure enough generalization. So this is really, really cool as a general idea. And of course, there are a lot of challenges. Some of them we are going to address today. And of course, if you have questions at any point, feel free to interrupt me or write in the chat. And I'm happy to take questions and answer questions also during the session. All right, so with a split of training and inference phase, how we're going to actually like train. And let's say the standard approach would be nowadays neural posterior estimation, where we are learning from simulated data, a generative neural network that can actually learn to approximate the posterior distribution for any potential input data. So for example, if our generative neural network would be a normalizing flow Q of psi, where psi are the neural network parameters, we would be using some kind of maximum likelihood loss. Often also we are coupling our generative neural networks with summary networks, summary architectures that are tuned to the specific data at hand. So if we have exchangeable data or independent data, we are using some set architectures, or if we have some time series data, we would be using summary architectures that are taking this time series aspect into account. So the summary network would always be specific to the kind of data we are dealing with, and the generative neural network would then try to do inference inference, that is, compute the posterior distribution given the summarized data obtained from the summary network. So the general maximum likelihood loss for normalizing flows would basically, we are trying to minimize both psi and zeta. And we are going to do this in a simulation-based way. That is, we are simulating from our joint probabilistic model. First, we are simulating from the prior, then we are simulating from our likelihood simulator, from our data simulator, and then we are minimizing the minus logarithm of the density of the approximator. And this is a strictly proper loss. That is, upon perfect convergence, we are going to have a perfect posterior approximation for essentially any kind of data that fits to that model. In practice, of course, we cannot evaluate that expectation exactly, so we are approximating it via samples from our model simulator, essentially. So that's where simulation-based inference comes in amortized Bayesian inference. So amortized Bayesian inference originally came from simulation-based inference, and we are now, also in my group, trying to move it a little bit semi-independently of that, so that we also do amortized Bayesian inference for likelihood-based models. But in general, we are still strongly relying on the simulation part, because the learning of the neural networks only takes place if we are able to simulate from our joint probabilistic model. Any questions about that so far? For most of you, this may be repetition. For some of you, it's maybe new, so don't hesitate to ask questions. Okay, so now to the parts of the talk that are a little bit more specific to concretely mixture and multi-level models. So a lot of Bayesian models, especially complicated Bayesian models, have a certain kind of factorization. So it's not that we have a bunch of data and a bunch of parameters, and all data is related to all parameters, but rather we have certain kind of structure in the data that permits certain kind of factorization of both the forward model, that's the one we are simulating from, and the inverse model, that's our posterior distribution. And this kind of smart factorization is something we're going to make essential use of today. So suppose we have some data variables y and two sets of parameters, which I'm just calling theta and tau right now, with the following forward model. So the joint distribution of all of our variables y, theta, and tau would have the following factorization. We would have first just the distribution, we could call it a prior distribution of our parameters tau. Then we would have another prior distribution of theta given tau. So we can think of tau as some kind of hyperparameters and theta as some kind of local parameters. We will make this more concretely in a bit. And then we are generating data y only conditional on the local parameters theta, but then independent on the hyperparameters tau. Yeah? So notice there's kind of quite strong factorization into this. It's not that all of these y, theta, and tau would be arbitrarily related to one another, but rather tau is just independent of the others, theta is just depends on tau, and y just depends on theta. Yeah? So that's in the forward process. This is how we would simulate from that. But more importantly, through this factorization, which we usually know since we set up our model like this, we also obtain simpler posteriors than just the joint posterior. So the joint posterior of all parameters, p of theta and tau given y, would perhaps be very complicated. But since we have, in this specific case, this very nice factorization of the forward model, we also get a very nice factorization of the inverse model, that is, of the posterior. So in this specific case that I show here, our joint posterior distribution of theta and tau would in essence be the product of the posterior distribution of theta given y, so far so good, and the posterior distribution of tau given theta. Because in the forward model, y was only dependent on theta, in the backward model, one possible factorization would be that theta is only dependent on y, and more importantly, tau does not have to be dependent on y anymore at all, because there's theta in the middle. Yeah? So if we know the posterior distribution of theta, we know the posterior distribution of tau without having to know the data for the posterior distribution of tau due to that factorization. And as a result, the posterior distributions that we are going to learn are much simpler. So we started with a highly joined complex posterior distribution of all parameters, but due to the factorization, we end up with two simple posteriors. One posterior of theta given y, and another posterior of tau given theta, given specifically the posterior distribution of theta. Yeah? And these kind of smart factorization of the posterior distributions, we are going to make heavy use of in this talk. Since this is kind of an important part, are there any questions so far? Simple idea, and we make good use of it in amortized Bayesian inference, essentially. Okay, so the first case I'm going to talk about is mixture models. That's a paper of Simon and me, which we recently put on arXiv, and it is currently in review. I will put the slides later on my website, so I don't know if you're missing the link or you just want to check something, it's going to be online on my website later on this afternoon. Okay, so if we are thinking of mixture models as graphical models that have this kind of specific factorization, we can, for example, look at it as the following. So we're changing the notation now, so a bit of flexibility. We have some overall parameters theta, and each of these overall parameters theta, they control the mixture indices z. So we have in a mixture model, more generally, we have each observation, if we take it simple, may belong to different kinds of groups, so different kind of mixture components. However, a priori, we don't know which observation belongs to which mixture component if we have like real data. But in observed data, we basically simulate forward. So we had some like overall general parameters controlling, how the general model looks like. And then conditional on these overall parameters, we have the individual mixture indices Z1 to, in this example here, Z3, which would control which of the observations 1 to 3 belong to which of the mixture components. And then after we have decided, or after it has been decided, which of the observation belongs to which mixture component, we're going to have like the actual data y1 to y3. So we see here in this kind of exchangeable example on the top, where we have independent mixtures, we see this already strong factorization of the forward model. Yeah? So theta is only related to z, but not directly to y. Yeah? So z is in the middle of theta and y, so this is kind of a strong factorization, which we later on can use. Of course, there's also some like other kind of structures in mixture models. For example, we could think of a hidden Markov model where the mixture value of, I don't know, the first observation or the first time point, say, would affect kind of where the mixture would be at the second time point, where the mixture would be at the third time point. So we would have some Markov property in our latent mixture indices Z, for example, in time series modeling, where, let's say, in a reaction time experiment, people switch between the state of being attentive and actually doing the reaction time experiment and being bored and looking out of the window. Of course, these are very different reaction time processes if they're actually looking or if they're, I don't know, in their thoughts or looking out of the window. And we would expect that there are some temporal correlations of these states, of these two different process states over time. And in such cases where we have mixture models in the context of time series, we would, for example, consider hidden Markov models. But then there, of course, is also like more even, different kind of factorizations where we don't have this directed structure where Z1 predicts Z2 and then Z3, but we just have a joint distribution. For example, in spatial modeling, where we had different regions, and the different regions could be like in different latent mixture states, and the regions would be dependent on each other because of their spatial adjacency. Yeah. So the point here I want to say is that mixture models could come with different kind of factorization. They could be exchangeable, could be some directed Markov model style factorization, or some joint distribution over the mixture indicators. But in any case, in all of these cases, we still have some strong factorization because the theta is only related to the y's through our z's. Yeah? So we are able to actually simplify our posterior distributions in a smart manner in order to make good use of this during ABI. Okay, so under the forward model, and assuming this kind of exchangeable independent observations, we would first sample from our hyperprior P of theta. So we would first sample theta. Then from the mixture index distribution P of z given theta, we would sample our mixture index, which would determine which observation belongs to which mixture component. Let's say which reaction time that was recorded belongs to the component people actually did pay attention and reacted accordingly, or people looked out of the window and were a bit passive. And once we have basically selected or like simulated the specific mixture component for observation, we are going to sample data, for example, reaction time, from that specific mixture component. So where P of Zi in the third line basically indicates this is the likelihood, this is the distribution of the data for the ith mixture component. Sorry, for the Z mixture component belonging to that observation. Okay. So I said that, now that we have the forward model, which has some strong factorization, we could use that factorization also for posterior inference. So what we are after in case of independent units here, like exchangeable units, is the posterior distribution of theta and z given all the data. Yeah, so that's always what we are after. And now in case of independent units, this can be factorized in different ways. At the start, I was introducing you to one factorization, but we can also use another. For example, we can say we are first going to learn our posterior distribution of what is now the hyperparameters theta, given all the data yij, where I indexes the basic observational units and j indexes the observations within the observational unit. So we would first learn the hyperparameters from all data, and then we would have a specific posterior distribution for the Z's mixture index, essentially, given now only the specific observation belonging to that observational unit and the overall parameters, the hyperparameters theta. So what we have gained from that is that when we are computing the posterior distribution of our mixture indices Zi, we no longer have to condition on all data. That was the case if we're using the unfactorized version, but we only have to use the data of that specific group and the hyperparameters. Yeah? It's a different factorization than what I showed at the start. At the start, basically, if I would have used the factorization at the start, I would have first learned the Zi based on all the data, and then I would have learned the theta based on the Zi. But the advantage of the factorization that I'm showing here is that and I will show this in a bit, we can have like very nice, we can design very nice architectures, neural architectures, to estimate these posterior components well and nicely in a way that it nicely amortizes not only over the number of observations within the units, but also over the observational units. So we can have, like, in theory, like varying length number of observational units where we are computing the mixture components. There's also inverse factorization for dependent units, but I'm going to skip this for now, because the general idea is we have that forward factorization, we are translating that into an appropriate inverse factorization, and if we do this properly, we are getting some nice neural architectures out of this. And that's what I want to illustrate now. So this is now when we are learning our neural posterior estimators in the training phase. So we are having the forward process, and we're learning that from mixture models. We would be starting first with our prior on the parameters theta, and then for each observational unit I from 1 to n, we would first sample our corresponding kind of mixture index Zi from the mixture index distribution, and then we would be sampling our data Yi from the corresponding likelihood given the specific mixture index and our parameters theta. And now the architecture comes in. So we're going to summarize. Someone did mute themselves. Okay. So we're going to summarize with a local summary network the data Yi of the specific observational unit I. And we're going to call that summary net, the local summary network, separately for each observational unit I. And based on that, we're taking this local summary network and we're doing two things with it. First of all, we are training also a global summary network, which takes and summarizes all the local summary networks results together. So the local summary network gives us a summary for each individual Yi, and the global summary network takes together all of these summaries of all the observation units Yi and like makes a big summary out of this. So we have this factorization already present in the summary networks. And then we have also a local and a global inference network. For mixture models, our local inference network is actually a classification network because our local parameters, the Zi, are just the mixture indices. So this is a discrete variable that just tells us which observation unit belongs to which mixture component. So based on the local summary network for the observational unit I, we're going to train a classification network based on kind of the true labels Zi and what the summary network tells us via some kind of, for example, a maximum likelihood loss. So here we have the local summary network feeding into the local inference network, which in this case is a classification network because we are dealing with the discrete parameters. But then we have also like the global inference network, which is fed by the global summary network that learns the posterior distribution of our hyperparameters theta. And as you can see from that architecture, we are making smart use of this different kind of factorization by having summary networks and inference networks that just use the specific kind of data we know they will use and not using any kind of other data that we know will be irrelevant based on the known factorization of the model we are going to try to learn the posterior distribution over. Questions so far? And then, of course, we can do the inverse process. So when we actually have observed data, here called Yi ops, after training, we can actually do inference and get the posterior distribution of both the mixture indices and of our hyperparameters theta. So we are basically feeding in our observed values Y ops into the local summary network. The output of the local summary network gets into the classification network. The local summary network also gives all the information to the global summary network, which then basically transforms this into a summary for the global global inference network, our posterior network, giving us a distribution over our hyperparameters theta. And then based on these posterior samples of our hyperparameters theta and the local summary and the local summary network's output for the ith observational unit, we're also getting posterior samples for the ith observational mixture component posterior distribution. So we see how both on the forward and the inverse model and training procedure, the networks are playing together in an efficient manner. And notably, with this architecture, we can have varying number of observational units. So this n, the number of observational units, can vary across data sets because we have amortized in a way that we can always have the local summary network, which handles always only the local information for the specific ith observational unit. So that's the general idea. We will see this the same actually for multi-level models. So when we now focus on some quick results to show how well this actually works, in this case for the Gaussian hidden Markov models, I'm skipping a little bit over that because I explained it already earlier, where we analyzed just one of the examples we have in the paper, a Gaussian hidden Markov model with two simple states, and then basically also some switching between them. And what we do see, just like just on a high level, is that after we have trained our neural posterior estimation with a specific factorization on this hidden Markov model, we see that the neural network inference is like very well calibrated. Yeah, so which we see on the first row. If things are well calibrated probabilistically, then we would see this kind of wiggly red lines to be within the gray area, which definitely is to be the case. And if learning is also properly, we would expect that our recovery, that is the accuracy of, let's say, the posterior distribution with respect to the true parameter values in a simulated setting, are well in alignment with each other, which is basically represented by the diagonal line down. So if you're familiar with these kind of papers, these are common plots we're going to see. So basically, the learning of these models has been, working efficiently here. And what is more, we not only get well-calibrated results, but we are also achieving basically with our mixture ABI approach, we're achieving the same posterior distributions as, for example, a gold standard like STAN would. Yeah? So in this case, the hidden Markov model is a model that has an analytic likelihood, so we can also run something like standard MCMC with STAN, and we see that we achieve basically, and we obtain the same posterior distribution as STAN, which gives us high confidence that we are actually able to learn the underlying true posterior distribution, even for new data unseen during training. So this was basically the with respect to the hyperparameters theta, which we call theta in this example. But of course, we can also look at the posterior distribution, so to speak, of our mixture indices. Yeah? So on the top row, you see for a specific kind of data set, the observations in dots, where then the colors indicate whether we are currently with that observation in the state 1 or state 2 in this artificial example. And without going much into the detail of the difference between filtering and smoothing, we do see that basically the posterior predictions with respect to the mixture components per observation of STAN and base flow align perfectly, regardless of what kind of filtering and what kind of dependency assumptions we're actually going to put into the model. In other words, we have been able to learn the posterior distribution over this kind of complicated model in a very, very good manner. Yeah, so in a very accurate manner. And now we could make use of the amortization properties. That is, if we had new data, the inference wouldn't run for, I don't know, several minutes like in STAN, but it would just essentially be instant, because the inference based on these neural posterior estimations are usually like very, very quick, fractions of a second, depending on the architecture. Sometimes a bit slower, but if we really want it, we get it in fractions of a second. Okay. So that would bring us to multi-level models, where we are going to see similar ideas at work. Are there any questions so far? Cool. So
I have
yes. Mm-hmm.
I have a question. How do you so thank you very much, first of all. How you amortize over the different numbers of observations in your model, in your neural network? So what kind of architecture do you use here? Yeah, and what are the limitations maybe also as well?
Yes. So first of all, in principle, it becomes possible to amortize over the different number of observational units, because the local summary network just handles individual observational units. So that's the prerequisite. That's why we're using this specific factorization. So the local summary network doesn't care if it individually processes 10 or 50 of observational units data individually. In practice, in training, we're setting up our simulator in a way that sometimes, let's say, we see n equal to 10 observational units, and sometimes we see n of 50 observational units. So we are training the network with different kind of number of observational units, essentially, so it knows the variation across this. Yeah, so this is the practical side. And on the more architectural side, if we are taking, let's say, an exchangeable model for now, for simplicity, we can use, for example, set transformers or deep sets that are essentially pooling the information for the individual groups, and can be set up in a way that they don't care how many number of groups we do have. Of course, we need to tell the inference network later on, look, this is inference based on 50 observations, not based on 10. But the summary architectures wouldn't mind if they're going to summarize 10 or 15 observations or observational units. That's essentially how we achieve that.
Okay,
in practice.
thank you.
All right. Good. So now, when you've understood this idea, we do the same in actually multi-level models, because it turns out they're actually very closely related. So this was work led by Daniel Habermann, and with contribution from Marvin Schmidt and Lars Kümmich and Andreas Bulling, and also from Stefan. So when we're considering multi-level models, we see it's very similar to the mixture models. I have just added another component and changed the notation a bit. I'm sorry for this, I wasn't consistent with this. So here now, for these multi-level models, I'm going to call the hyperparameters tau. The local parameters are going to be called theta, in this case for 3 groups, theta 1 to theta 3. Our observations are continued to be called y. And then we have some shared parameters, sigma. I want to quickly fill this with life. So think about, we want to do inference on the, recovery probability of certain complicated diseases, depending on which hospitals people go to. So then we would basically have our groups, which would be in the individual hospitals, and the theta 1 to theta 3 would be the recovery probabilities for that disease in hospital 1, hospital 2, and hospital 3, respectively. And tau would be some general hyperparameters, providing information that is applicable basically to all hospitals. But what we often do have is also like some additional parameters, sigma, that are basically shared across the hospitals. Let's say we would assume that there's the same kind of noise happening in all the hospitals, because they're using the same kind of, measurement procedures of certain kind of disease progression, etc. So we would not only have these local parameters and the hyperparameters tau only affecting the local parameters, but we would also have some shared parameters. But as it turns out, basically, whether we have shared parameters or not doesn't really matter, because we are able to summarize the hyperparameters tau, the shared parameter sigma together, and then the architecture essentially looks the same as in the mixture models. So here's a plot from the paper we are using, and it looks a bit different, but the general idea is the same as we have in the mixture models. So we have some hyper or shared parameters tau and sigma coming from a prior in the forward model, from our global prior. Then we're having our local priors for our individual, like group-specific parameters theta, for example, for the 3 hospitals or 3 subjects, 1, 2, and 3. From that, we are going to have like subject-specific or group-specific data y that enters our local summary network and also enters our local inference network. So for multi-level models, usually also our local parameters are continuous. So our local inference network would no longer be a classification network, but also a generative neural network, for example, a normalizing flow. So my phi2 would basically be our local inference network, and h of psi2 would be our local summary network. And that local summary network would not only inform the local inference network, but it would also go ahead and inform the global summary network, which in turn would inform the global inference network, then learning the posterior distribution of our hyper and shared parameters tau and sigma. So the general idea is the same. We have kind of a smart factorization of the posterior based on the known factorization of our forward problem, and we are devising the summary and the inference architectures in a way that they are playing most efficiently together, in a way that we can provide weight sharing while still being able to amortize, for example, over the number of subjects, over the number of groups, etc., through the same process I just explained to the question. Yeah. As an example, just very quickly, we looked at European air passengers traffic using a time series model where we had a bunch of parameters. So essentially some kind of autoregressive model with a bunch of predictors, which we could also like fit in standard MCMC, for example, but we have also more complicated examples in the paper. I'm just presenting this here because I believe it's kind of, quite intuitive. So we're essentially predicting how the air passenger traffic in Europe is changing over some years as a response to, I don't know, changes in economic situation, etc. of that country. And for each of the countries, we're going to have actually 5 local parameters, some intercept parameters, then some autoregressive parameters, additional coefficients for predictors, as well as the log residual standard deviations, all being estimated locally. And then, of course, we have some global parameters, which are the hyperparameters of these local parameters, which I'm not going to show here for simplicity. So after training, this is essentially how it looks. For example, if we are training our amortized Bayesian multi-level framework and then start making predictions after, let's say, the 5th or 6th year, we see basically that the predictions that are here shown in these lines match very well to the actual observed data in this point, unseen by the model, that we see here as specific points. So we get predictions through our amortized inference network for all countries, but if we were interested in that, we would also get estimates for the local parameters, and we would get estimates for the global parameters, or like the posterior distribution of the global and local parameters. Basically, essentially instant. So when new data would come available, let's say we had like a new year or new data, we could just ask our architecture, please give us also inference and predictions, posterior predictions for the new data with the new year, and it would give us this information almost instant, so we didn't have to refit the model at all, actually. Also here, we managed to get like really good uncertainty calibration, at least on the training day and in sample data. We also got very good recovery. So given sufficient data, we are actually able with our posterior approximators to estimate the underlying ground truth parameters very well. Okay. Also here, as a validation, this relatively simple model, we could also fit with STEN. So we did comparison with STEN. On the top part, you basically see the posterior distributions of the individual parameters, the alpha, beta, gamma, delta, and log sigma, where the individual local parameters. So in each of these 2 lines indicates a specific country. And as we do see, our MLNPE, that is the amortized multi-level model, essentially produces the same marginal posteriors as STEN does, with a little bit of variation. And also in terms of how much shrinkage we are inducing in the local parameters through our multi-level structure, we see that this very well aligns with STEN. So one reason why we do multi-level models often is not only because the factorization is nice, but also because we don't want the individual, like the local parameters, just to be informed by the local data, but we actually want to share and pool information across all the groups. So we want to have some shrinkage of all of the group's parameters together. So we need to investigate if this amount of shrinkage is actually comparable or is actually kind of matching what we want to have. And we do indeed see that the shrinkage that is implied by our amortized inference procedure matches that shrinkage of STEN also here very well. So for this model, we were able to like really recover what we believe would basically the true analytic posterior here as gold standard reference with STEN. In practice, of course, we wouldn't fit STEN because we just wanted rapid inference. This is just here to showcase that we are actually getting the posterior right. Okay, so to summarize, multi-level mixture models, we looked at simple multi-level and mixture models, follow simple probabilistic factorizations. And when we are utilizing these factorizations, that enables amortized Bayesian inference that can be amortized across a varying number of observational units and observations within units, while, and I didn't talk about specifically, keeping each of the individual inference networks and summary networks small in size. Neural ABI is a really cool field. I'm very excited to work on it in the past couple of years. However, much of the potential of neural ABI is yet to be realized. And whoever is interested in working with us on any of the topics related to neural ABI, please reach out to us and we would be more than happy to work with you. Thank you.